to go back and review. Okay, so what we're talking about today is the new version. Oops. Sorry, give me a second to get set up. All right, there we go. Sorry about that. I had closed my PowerPoint. What we're talking about today is the new version of FACS, which will be called FACS 7.1. Sorry, I'm frozen. Okay, it'll be called FACS 7.1. I'm going to present something about platform trials at the beginning. Then Elias is going to go ahead and talk about some changes we've made to core. There's a couple of new endpoint analysis models for dichotomous designs that affect both core and platform trials. We've made some modifications to the dose escalation engines. Specifically, we've changed how we go about even starting a dose escalation design. Elias will talk about that a little bit, and then he'll talk about some of the rule modifications and added flexibility that we've put together for dose escalation that hopefully make it more one contiguous engine that you can use for everything, rather than a bunch of different possible CRM engines wasn't always easy to know which of those you should go into. And then Praveen is going to talk about some quality of life upgrades that we've made. We've added some tools to help plot. We've changed some things in FACS that hopefully make it easier to use, and he's going to go through a bunch of those in detail. The scope of this is, well, so FACS 7.1 is not released yet. It's planned to be released in the next month or two, so end of July is the target. So that's when you'll have access to these features. I'm going to talk about, again, concurrent controls in a platform trial. The platform trial engine kicked off last year with FACS 7.0, and it was and remains a pretty simple platform trial simulator. You can simulate arms coming in and leaving. You could do early success and futility for specific arms, and you can fit a pretty simple model to the arms, and we've restricted the modeling to essentially each arm having an independent model. The only thing you could do in FACS 7.0 was use all control patients in the analysis of every arm. So I put on the right-hand side here a figure where on the x-axis is the duration of the trial, and each of the arms has its own horizontal line, each of the arms in the platform, and the bottom line is the control. You can see that in this perpetual platform, the control arm is enrolling all the time, and then other arms that are in the trial come in and leave on sort of their own schedules. And so I'm going to focus on these top two arms, treatment 4 and treatment 5, almost this whole time I'm talking. And the only thing you can do with FACS 7.0 is to use every control that's been randomized in the platform when you do the analysis of treatment 4 and treatment 5. We've added the ability to restrict that analysis to only control subjects that were randomized while a treatment was being accrued in the trial. Okay, so I'm going to talk a little bit about that. Here's some highlights. So for treatment arm 4 and 5, you see that for the all controls model, we use every single control randomized in the trial. And for the concurrent control model, we only have this small subset of the entire control arm highlighted in green would be used to compare to this arm if it was fitting the model using only concurrent controls. Okay, I'm going to switch over to facts and show you a little bit how this works. I designed a really simple platform trial in facts. Smaller so you can see. I designed a really simple platform trial in facts. It's not even adaptive in the sense that there's no updates throughout the trial. There's no interim analyses. It's just an arm enrolls, and then we do an analysis at the end of that arm's time in. I'm going to simulate 150 patients per treatment, a continuous endpoint where a high response is good, and I'm inventing this endpoint as we go. We're going to fit 5 total arms, and then the platform is going to end. And I've set it up so that the first 2 arms, like the figure we were just looking at, the first 2 arms start at time 0. Treatment 3 enters at 6 months, 26 weeks, half a year. And then the arms we care about, the only arms I'm going to look at, start later in the trial, a year after randomization to the platform begins. So they're set to enter earliest possible time, 52 weeks, latest possible time, 52 weeks, meaning they're going to enter right at 52 weeks in this. I've renamed the treatment arms, treatment 4, all controls, treatment 5, concurrent controls, because that's the comparison we're going to do for each of those arms. So I'm going to set this up so that we estimate a concurrent model and a treatment, an all controls model. And then treatment 4 is going to make decisions based on all controls. Treatment 5 is going to make decisions based on concurrent controls. And we're going to do a little analysis of how that difference in the models changes some operating characteristics. I set up some simple scenarios where in every scenario, the control arm has a mean of 100 and the subject level standard deviation is 10. So again, I'm inventing this endpoint. There's a null scenario where every treatment has no effect. So the fixed mean effect is 0. There's no difference between any of the treatments and control. I set up an all good 2 scenario where every treatment has a 2-point benefit. So it's 1/5 of a subject level standard deviation. And then an all good 4 where every treatment has a 4-point benefit on this endpoint. So in reality, control has 100 mean. Treatment 1 through 5 have 104 mean in this case, is what this is saying. I specified a quantity of interest. So this probability of theta D is greater than theta control is a default QOI that's there when you set up the trial. It's just what's the probability that each treatment arm has a greater mean than the control arm. I added a QOI, and now you can choose analysis population in that QOI. I'm realizing that you can't see that probably. So let me share my whole screen for a second. So when I click add on the QOI, this pops up, which you couldn't see before. And it allows you to choose an analysis population, either all controls or concurrent controls. And so every QOI in facts, including predictive probabilities and p-values, will allow you to select the control population you're using. I'm going to select concurrent controls with the mean on the mean, which is the only thing you can choose in a continuous case. And I can ask for, I want my treatment to be greater than the control arm with no delta. Okay, so this is just the probability of superiority, QOI, simplified down to only use the concurrent controls. And that's the QOI I've added here. Okay, so that's the only 2 things we're going to calculate. Again, really simple. And in the design, I've set up non-informative priors with, mean of 100 is what we expected, and a large standard deviation. So 25 standard deviation on the mean. That's for the all control model. For the concurrent control model, I have the same prior on the control mean, and I've set this include participants up to blank weeks from treatment entering trial to be 0, meaning that I'm only using controls exactly at the time of entry of a target arm to fit that concurrent control model. If I was to set this to, say, 10 weeks, it would use concurrent controls and non-concurrent controls that were within 10 weeks of an arm starting randomization in the concurrent analysis model. Okay, so that allows me to be flexible with what I consider a concurrent subject. And then finally, the treatment response is also a non-informative model. I have fixed allocation, so I'm 1-to-1-to-1 for all K arms currently randomizing. And I've only set success futility criteria for the 2 arms that I'm going to pay attention to. For treatment 4, I have this all controls QOI compared to 0.975 at the end of the trial. And for treatment 5, I have the same probability of benefit QOI, but only on concurrent controls. Okay, so the treatment 4 is all controls, treatment 5 is concurrent controls, and I've already simulated this design. And I'm being overly simplistic here and not simulating a very complicated trial, but the result of this, as we know, when you get more control patients in the all control model, you're going to have higher power. And so you can see here that I simulated the type 1 error. This is only 2,500 simulations, so this should be 0.025. There's actually a fair amount of variability in that, but it's just based on the simulation variability. The power in the all good 2 scenario that you can see on the left is 40% in the concurrent controls arm. So this is a decision made only using concurrent controls, and it's 55%-ish using all controls. So we got a power boost there. Also in the strong effect scenario. I can look at a plot here and get a quick back and forth of what I think is happening to the QOIs. So just to see the shift on average of the QOIs. Now it's bigger. It's plotting a fair amount of data. I'm looking at the QOIs for the all controls analysis right now. And as I change this to the concurrent control analysis, you should see the box plots move down away from 1. Which, yeah, so that one went down. This one went down a little bit. The null scenario actually didn't change much, and it shouldn't, because we should still have roughly uniformly distributed probabilities in the null case. Okay, so we can see what we already knew, that the QOIs actually moved down in that case. A couple of other things that I can showcase that aren't directly related to the example, but they're new in FACS 7.1. The open in R function now works a little bit differently. I'm just going to open the simulations file in R. If I click load, it boots up RStudio, and it has this function called read.facts. Nothing loads into my environment now. This is already there. So nothing loaded into my environment. It just gives me code that I can run. And now simulations.df has been loaded in, and this has 2,500 rows, and I can now manipulate the data from facts. And so I think we've streamlined how you can get data out of facts and into R a little bit, which is nice. We also have this compare scenarios in AIRSHIP, and Elias is going to talk more about this, but we have this R package Shiny app called AIRSHIP that allows you to take the output from facts and load it directly up in this Shiny app that's meant to essentially create more flexible plots than we currently have in facts. So I'm going to actually go over here once the data is loaded. I'm going to simplify my example a little bit and take from 5. I only want QOIs greater than 0.7. I'm subsetting the data to make the plot nicer. Okay, and then I'm going to go over to the left side, shows the different plots you can make, and you can explore this as you start to use AIRSHIP. I'm going to make a scatter plot just to show something, and it starts with kind of a default plot that's very boring. but I'm going to select some new axes. So on the x-axis, I'm going to take QOI underscore 115, which is just the concurrent probability of superiority on the x-axis, and the y-axis, I'm going to move the probability of placebo using all controls. The only thing I want to show here is that the all controls model tends to be higher. The all controls model probability of superiority tends to be higher, especially if I facet this by response profile, where the null is on the right. The best scenario is in the middle, where there was like 99% power, and then the moderate scenario was on the left. So we expect to see more points near the top of this graph because the all controls plot should have higher probabilities of superiority. And it's hard to see there, but it does focus, especially at the top near the probability of superiority for the all controls arm being slightly better. You can see it here where there's. Okay, so this tool, AIRSHIP, will be available to use. It's a separate R package that FACS links with, and so you can actually use this without FACS. You can use it to process any simulations and to create some plots. The code is shown below if you want to recreate the plot based on the data, and you can look through what's actually in the plot. And so, okay, so that's the big change to platform trials, is that you can actually run that concurrent model. There's no facilities to simulate to simulate a change in the control arm yet. That's coming, but you can only do fairly boring stuff with the all controls and concurrent controls until you can actually change the control arm, which is where things get interesting. So we're planning to allow you to create some, wiggle in the control arm over time if you want there to be an increase, decrease, something like that. And with that, it's kind of necessary to allow for modeling of changing in the control arm over time. So we're planning on adding the Bayesian time machine. That's a flexible, smooth time trend estimating model, and the time categorical model that just for specific time bins in the trial, it independently estimates how well or poorly the control arm is doing in that interval. Okay, so that's it for me. I'm going to pass it off to Elias to talk about some dose response models and the new CRMs.
Great, thank you, Nick. I'll just take over sharing the screen from you. Perfect. Okay, so I hope you can see my Windows screen now. The first thing that I want to mention that Nick already mentioned before is that we've made some changes to how we can analyze dichotomous endpoints. So to demonstrate this, I've created a very simple core design with a dichotomous endpoint. To show you there's no adaptivity in here. We set 100 patients for this trial, and we have two arms. One of them is a control arm, one of them is a treatment. And basically there's two response scenarios that we investigate. One is a null case where both of them have 10% response rates. And another one is an alternative where the control has 10% response rate and the treatment has 30% response rate. We have 5 patients per week, not that it matters much for this example, but just for completeness. And then the first thing I want to highlight is that here in the design tab, under dose response for the model, there's now this option to choose independent beta-binomial model, where we have independent priors for each of the different treatment arms, and then we have a standard beta-binomial model. And then the posterior probabilities are calculated that the beta distribution of, say, the treatment arm is larger than the beta distribution of the control arm. I've also gone ahead here and in quantities of interest, I've set also a p-value to be calculated. So this is a very standard p-value that's based on a normal approximation. And for this, and I've used this as a decision quantity in my trial, where I declare success in the end if the p-value is smaller than 2.5%. So I've also gone ahead and simulated this for both the alternative case and null case. And one thing that I want to show you here is also how we can visualize these results in AIRSHIP. For that, I'm also going to click on Explore Results and then click Compare Scenarios in AIRSHIP. This loads the aggregated simulations file that I've created previously. We can see how AIRSHIP is loading up. I'll just let it wait, let it finish reading in the data. The data has finished reading in. So the first thing that I want to have a look at here is I want to compare the different response profiles, and I want to show how the p-values are distributed. So this is a result that you might be aware of. In the null case, we have a uniform distribution of p-values. We can very nicely see this here with the box plot. And in the alternative case, we can see that the p-values are much more often close to zero, and therefore we reject the null hypothesis. Another thing that I want to show here is that, so remember we specified the Beta-Binomial model and we specified p-values. So I want to have a look at how these sort of compare with each other. And for that, I'm going to click on the scatter plot tab. And here on the x-axis, I'm going to plot the p-value. And on the y-axis, I'm going to plot the posterior probability that the treatment arm is better than control, which is this one. And an interesting thing that we can see here is that this basically is a diagonal. So, I mean, the variation that we see here is just because of the number of MCMC samples that we took. But basically, we see a diagonal here, meaning that the smaller the p-value, the higher also the posterior probability that our treatment is better than control, which is expected. And one other nice thing that we can see here, so to illustrate this, I'm also going to go back and filter the data. So I'm only going to look at somewhat small p-values. So let's say I'm only interested in p-values that are smaller than 0.2, roughly. So I'm recreating this graph. On the x-axis, we put the p-value, and on the y-axis, we put the posterior probability. And then let's also color this by outcome. So remember that we decided to declare success if the p-value was smaller than 2.5%. So this is exactly what we see here. This white line, I'm not sure you can see it on your screen. I can see it on mine. But there's a white vertical line here that basically separates these into trials where in the final analysis we declared success and trials where in the final analysis we declared futility. And this is how they're colored. And we can nicely see that if we follow this diagonal, this basically goes through all the points where, for example, if the p-value is 0.05, the posterior probability is also 95%, which is generally nice, and this is what we would have expected because we specified vague priors here. Okay, that's it for showing the Beta-Binomial model. One other thing that we added for dichotomous endpoints is in the quantities of interest tab. When p-value QOIs are specified down here for p-value calculation method, we now have two options. There's a normal approximation and there's Fisher's exact test. So in this particular, for this particular simulations, I've chosen the normal approximation. Let's have a look. We had about 70% power in the alternative, and we had about 2.5% type 1 error in the null case. Now I'm going to open up the exact same design where I've used Fisher's exact tests. And this is already with the pre-simulated results, so you don't have to wait. But what we can see here is that the power now is slightly decreased. It's now 63% as opposed to the roughly 71% that we had before. And also in case of the null, the type 1 error rate is reduced. And that's because Fisher's exact test, as we know, is more conservative. Okay, that's it for the dichotomous endpoints. The next thing I want to mention is that we've made some updates to the CRM dose escalation engine. For this, I'm going to firstly bring up some slides. I will show this also in facts later, but one thing that I want to point out in the very beginning here is that we have now 3 different Q concepts for open enrollment in CRM. So we have a Q that's called maximum subjects without final results if dose is uncleared. We have a Q that's called maximum subjects without final results if dose is cleared and below MTD. And we have a third Q that's called maximum subjects without final results if dose is cleared and at MTD. And I'm going to show you a few examples what these mean. So remember, we have the option to allow backfilling in CRM, and backfilling basically happens when we are at a certain point in our escalation. Let's look at this example on the top right here, where assumingly we've escalated to something like 120 milligrams. We've assigned 3 patients. So in this example here before, I've set the maximum subjects without final results if dose is uncleared to 3. This dose hasn't been cleared yet, and 3 patients have been assigned. So we're not confident assigning any further patients here. And this is when backfilling can kick in, where in this particular case, we allow backfilling to 80 milligrams, as opposed to not enrolling this patient. So you can see that this queue of maximum subjects without final results if dose is uncleared is somewhat linked to backfilling. So if we hadn't allowed backfilling here, this patient would have simply not been enrolled. But since we allow backfilling, this patient was enrolled. This is just a reminder. This isn't new to fact 7.1, but for backfilling, several different rules can be specified. One of them is, as you can see in this example, this dose, 80 milligrams. In this here was the first time where we backfilled. We didn't backfill previously in the dose escalation. So this is, for example, one of the rules that we can set. One thing that is new to fact 7.1 is the concept of front filling. And that is, if we look at the example here on the right-hand side, we're at about 90 milligrams and we've assigned 3 patients here. And by the time the next patient arrives, we have observed DLT results of the first of these 3 patients. So in the graph below here, you can see the first dot here is green, meaning 1 patient on 90 milligrams did not have a dose-limiting toxicity. And if we allow front filling, that means that we assign another patient now 90 milligrams, as opposed to not assigning this patient or backfilling. And why did we assign this patient here? Well, if we go back to the Q length, remember that we allow the maximum subjects without final results if dose is uncleared to be 3. But this is the maximum subjects without final results. So in this particular case, before we assign this patient to 90 milligrams, there were only 2 patients without results. So we can assign a third one, since 3 is the Q length that we specified here. Another thing that I want to mention here is we have this Q concept of maximum subjects without final results if dose is cleared and at MTD. And that comes into play if at some point in our dose escalation, we started de-escalating again. So now, for example, our model thinks that something like 120 milligrams is our MTD. And we've already assigned 3 patients here and we're still waiting for their results, but we're at the highest dose, which we currently think is the MTD. So this patient here, this blue patient here, was not assigned to this dose anymore because we only allow 3 patients without final results if the dose is cleared and at MTD. And the third Q concept here, the maximum subjects without final results if dose is cleared and below MTD, is something that will come into play for backfilling. So we would only allow 6 patients at the same time being backfilled somewhere without having their results. Last thing I want to mention, and then I'm going to show you how all of this looks in facts and behaves in facts, is for stopping rules, we've added the concept that there's something like near doses. So in the example that you can see here on the right, we've stopped the CRM and declared a certain dose, the MTD, despite having only 2 patients observed on this particular dose. And that is because for the purposes of stopping the CRM, we've decided that we can also sort of count patients on the dose above and on the dose below, because they're considered sufficiently near that we don't need to enroll many more patients on this one dose in between. Okay, let's have a look at that in facts. So maybe the first thing that I will mention is I'll just open up facts from scratch and show you how the new starting screen looks like. The reason why I'm starting facts this way is because it's not released yet and it's just a development version. But we can see here that in those escalation designs, we only have a CRM engine and we have a 2D CRM engine, but all of the other CRM engines are deprecated. And basically all of their functionality is now covered in this one CRM engine. So that's the one that should be used for your CRM designs. So I'm opening up the one that I've sort of already pre-populated with some settings. This is very similar to what I've shown you before, where I've set the queue lengths exactly the same way that we discussed before. I'm targeting an MTD, so I'm targeting a toxicity of 25%. I have 9 different doses, and I allow backfill from the very beginning, and I also allow front fill from the very beginning. And I want to stop the CRM if there's 12 patients near MTD, and I count the dose above and below as near for the purposes of the stopping rule. So let's have a look at how such a trial would have played out. You might know this particular graph here. I like it very much. It's called the per simulation allocation history, and it basically just shows you a movie of how the different patients were assigned over time and what their results were. So let's have a look here. The first 3 patients were assigned to dose 1, and now we're waiting for the results. So these X's mean that these patients weren't assigned because we're still waiting for results of these patients. There's a particular point in time where we have the results of all of these 3 patients. None of them were, none of them experienced the DLT, which is why we decided to escalate here. And now we're assigning 3 patients to dose 2. The first thing you can see here is that after the 3rd patient was assigned to dose 2, when the next patient arrives, this patient is backfilled to dose 1 according to the rules we've set before. So we're assigning 2 patients, and by the time the next patient arrives, we have the results of the 3 patients in dose 2. One of them had a DLT, so we're staying on this dose. We are assigning 1 more patient for backfill. And the next patient that arrives is again not assigned, and that's also due to our backfill rules because we said that we do not want to have more than 6 patients per dose through backfill. So the next patient would have, so there's already 3 patients here. There's 3 patients in the beginning, so the next patients would have exceeded this limit of 6. This is why the patient is unassigned. One thing that we also see here is that we decided to not assign this patient to dose 2 because there's already 3 patients waiting here for their results. So this is this queue that I've mentioned before, the maximum subject without final results if dose is cleared and at TD, because we currently think this is the MTD, so we're not assigning more than 3 patients. But as soon as the first patient here has an outcome observed, we can assign another one. So this keeps going. At some point, we decide to escalate. We observe a few more patients, and at some point we decide that this is our MTD. And we can see that we stopped assigning patients here when there were at least 12 patients observed on those 3 and those 2. So it counted the patients on those 2, it counted the patients on those 3, and as soon as there were 12 patients observed, that's when our stopping rule kicked in, which we specified as 12 subjects near MTD, and that's when we stopped the trial. So I will just show you one more example here of front filling. So this is the exact same design. This is just a different trajectory of the simulation. And what we see here is that by the time the 4th patient arrives, the first patient had their outcomes observed, which opens up 1 spot in the queue because our queue was length 3 of subjects without final results if doses uncleared. So 1 spot here became available after this patient had their outcomes observed, and that's when we front fill a patient here. So that's what front fill is. Another patient was front filled here, and just to very quickly take you through the rest of the simulation, we have a few backfills, we have some more front fills, and at some point we decide that dose 4 is the MTD. And again, it was able to stop here, despite us having set that we require 12 patients near MTD, because we consider the dose above and the dose below near, and that counts towards this cap of 12 patients. Okay, thank you. And I think I'll pass over to Praveen for the rest of the new features in Fact 7.1.
Perfect. Thank you, Elias. Just going to share my screen. Okay, hopefully you can all see my currently blank screen with a couple of facts icons. Perfect, thank you. Yeah, so as Nick mentioned, we've made, and I love the way he phrased it, we've made a lot of quality of life improvements to facts in Fact 7.1. So how this came about, over the past year, we've been talking a lot to our facts licensees, trying to get some feedback on their use of facts, how they find it. And some common feedback that we got across licensees was that facts is tricky to use when you're exposed to it for the first time. Understandably so, because facts is a generic tool for creating all sorts of different designs. So we expose a lot of different options, and it's not always clear what these options do and their impact on the rest of the design. A big part of that is because obviously that we can't be too verbose in the way we describe checkboxes in facts. It just makes the GUI somewhat unreadable. But the trade-off there is that maybe it's not as clear as it could be, especially for someone starting off using facts. The other problem is that the other feedback that we got from licensees is that facts sometimes does not expose enough information, or maybe that, not that it doesn't expose enough information, but maybe rather the information is not exposed in a clear enough or user-friendly way. And that was another piece of feedback that we've been trying to address in 7.1, making the data that facts generates more transparent to the user, something that they can retrieve themselves and maybe post-process. So I thought I would show some of these features by creating a very, very simple dichotomous design, starting off with a fixed, and by fixed I mean non-adaptive trial with a frequentist calculation at the very end, just a p-value check. And then moving on from that kind of design to a adaptive design where we have some interims where we'll have some Bayesian decision rules that we'll be evaluating, in this case, posterior probability of success. So I've just opened up a core dichotomous design. This is just the template you get when you open core dichotomous for the first time. And one of the big changes in Fact 7.1 compared to the previous versions is that with the mouse, you can hover over options. So say enable adaptive features, and you're going to be presented with a tooltip explaining what this checkbox is about, giving some a basic description of it, and maybe telling you what's going to change in the GUI as a result of checking it. So, for example, here it says that if you check the enable adaptive features box, you'll have some adaptive options that will appear. There'll be new subtabs on the design tab, which is here. There'll be a way of specifying the definition of interims, the stopping criteria, allocation, and if you go through the other options, they'll have their own tooltips. So this is work in progress. We've started with core continuous and core dichotomous, but the plan with future releases is to have tooltips for practically all of the options across all design types, in fact, just to make the experience of using facts, especially for the first couple of times, much easier. So in my case, I just want to create, as I mentioned, a fixed design with a p-value calculation at the end. I've done a little sample size calculation where I expect the control response rate to be 35%. One of the active treatments I'm going to create to have a 65% response rate. And I've powered the trial so that we observe that treatment effect with 80% power. So it ended up being 50. I'm going to create 3 arms. So it's going to be 52 subjects per arm. So a total of 156. Going to the treatment arms tab again. When I hover over the add option, I'm told what it means to add a arm or dose into a trial, a description of what happens, some of the actions I can take as a result of creating these doses, namely renaming them. So I'm going to create 2 arms. Just going to call this treatment A, treatment B. Again, as I feel like I'm done with this tab, and as I move on to what appears to be the next tab on the list, if I hover over it, I'm given, again, a description of what this tab represents. So the virtual subject response is the place where I specify subject responses. So that's exactly what I want to do now. I want to create a null scenario with no treatment effect, and then I'll create one alternative scenario. Tooltips appearing again here, telling you that this scenario, this response profile that I'm creating is going to be combined with some other profiles mentioned that you create later to form simulation scenarios. So let me quickly create a null scenario here. Response rate of 0.35 across all arms. I'm just going to create one alternative scenario for the sake of time. I'm going to call that a 65 alternative scenario. Okay. Moving on to the next tab, the execution tab. This is the place where the subject accrual and rates and the dropout rates are specified. So I don't want to consider any dropout rates in my first pass. I just want to specify the accrual. And I expect there to be on average 6.5 subjects recruited per week, which takes us to an average duration of 24 weeks for this, for the fixed trial. Lastly, so moving on to the next tab, the quantity of interest tab. This tells you that this is where you specify the quantities that need to be calculated for the analysis. In our case, just the final analysis at the end for our fixed trial. So this is where I want to go to specify my p-value to be calculated. So I'll just create one here. Get rid of anything that I'm not interested in. I'm also told when hovering over the decision quantities that this is the place where I specify my decision rules to be used in the stopping criteria, including the final analysis. So I'm just going to create my p-value and take the minimum p-value over all the doses. And we're just going to do a p-value calculation for now. So we're not interested in the dose response tab. I'm going to go straight to the success futility criteria and specify my conditions. So I'll declare futility if the p-value is bigger than 0.025. Conversely, declare success if it's smaller than 0.025. And I'm just going to have on the allocation tab, a block size 6 equal allocation. Okay, so I've got my scenarios that I can simulate, the null scenario and the one alternative scenario I created. I'm just going to simulate 1,000 simulations here, which will happen quite quickly. Okay, so one of the changes in that 7.1, which wasn't there in previous versions, is the addition of the proportion of overall success column and the proportion of overall futility column. For the null scenario, this allows you to quickly see that the type 1 error, so the false positive rate, is controlled 0.025, and we've powered our alternative scenario so that we have around 80% power. We have some simulation error here. These columns allow you to quickly see the values you're interested in. This is a fixed trial, so before having these columns, we only reported the early success and later success. And for adaptive trials, you would have to add those two values to be able to get the overall success and overall futility. But we're making your life easier by adding these columns. Another thing that we've added in 7.1 to make your life easier is a cumulative operating characteristics graph, which allows you to quickly see the proportion of trials that have ended at a given time. So this is a fixed trial where our accrual follows a Poisson process, and that explains the shape of the graph here. Let me bring this down. We've added the ability, in fact, for any graph that's being shown, so both results graphs that are being shown here, as well as ones that pop up in the design, to have an export options button, which allows you to grab the data that's being shown in the graph. So I can export the data that you see in this graph into CSV. Giving it a couple of seconds to open up. Shows you all of the data that was used to plot that graph. So in addition to that, you also have the ability to save this image or to copy this image to clipboard if you want to add it into your Word document or somewhere else. So I'm going to update our design now to have some adaptive features. And now our dose response model matters. I'm going to use our new factor 7.1 beta binomial model using 0.5 as my prior. And I want to have two interims, one at 50% information, so that's 78 subjects, and then 75% information, so that's 78 subjects. And what I want to do here now is at the two interims use a Bayesian posterior probability to potentially end the trial early. So I'm going to have to go to my quantity of interest tab, create a new decision quantity, which is going to be the posterior probability of success evaluated, grabbing the maximum probability across all doses. So I'm just playing around here. I'm going to choose a futility criteria of the posterior probability of success to be smaller than 0.1 to declare futility at the interim. And we'll be a little bit more careful with the success criteria. And I'll set this to 0.99. So resimulating. A few seconds. We can quickly see now how the overall success has changed in this case. So we can see there's been a bit of type 1 error inflation in the null case as a result of having the success criteria at the interim, and power has decreased a bit, but we've had the number of subjects has decreased quite dramatically. So in the null case, we've decreased it by, on average, 6 subjects, and in the alternative case, our mean number of subjects has decreased by about 40 subjects-ish. And with the operating characteristics graph, you can have a look at how that's the effect of having these interims on the duration of the trial. And in particular, you can also have a look at the cumulative proportion of subjects that have stopped at each of those 2 interims that we've had in our trial. One of the changes we've done in factor 7.1 is the ability to have tooltips on the graphs themselves, so you can actually see the numbers here instead of guessing what it is. So at our first interim, it looks like we've had 41% proportion and 64% at our at the second interim or the first interim. And you can download this data again, gives you all the information you need. Okay. In the interest of time, I'm going to move on just to talk about what's next in line for us. So we're planning to release factor 7.1.0 maybe mid to late July, early August at the latest. well, the changes that were mentioned so far. We're going to have a 7.1.1 release, which we plan in October of this year, where we're going to revamp all of the equations in facts so that they're a little bit clearer. We're going to add some more tooltips. We're going to update the facts landing screen. So it's going to be a GUI heavy update. We're not expecting any engine changes for this for the 7.1.1 release, but it's going to be a substantial release in the sense that it's going to make the facts quality of life much, much better. For some of the stuff we have lined up for facts in the future, we are planning on adding a longitudinal model in our platform trial simulator. There's a new ordinal endpoint, which will be available in Facts Core. We're also planning on adding a lot of new dose escalation engines, i3+3, BOIN, and MTPI2. We're going to extend the concept of design variants. So the facts file will represent more than just a single design, but rather a collection of designs. And you can now easily, within this single facts file, compare various designs. We're going to start work on facts wizards, which will be a way of streamlining the creation of some common designs within facts, namely group sequential trials and Goldilocks designs. And later on, we'll be starting work on adding, creating a centralized place, web-based area where we'll have facts documentation and provide a place where facts licensees can come on to find the information they need for their particular trial. Elias, Nick, is there anything you would like to add to this?
Just that on the last side, it has slide, it has contact information for us. And if you email, I guess, facts@berryconsultants.com, it sends an email to us, to the development team, and me, Praveen, Elias, Tom are the ones that will get that and reply to you. So don't hesitate to reach out and ask questions, whether they're statistical or, you know, what does this button do? We'll get back to you quickly, generally. So.
Perfect.